This video is made up of parts from 4 other older videos that I had because I want to talk about the Poisson distribution, but I want to start from the very beginning, and there are a bunch of other things that I have to say first, mostly about binomial distribution. And the 4 original videos are still linked in the description if you want to go see them. But in here I've tried to summarize the basics as much as I could because the other videos had exercises and things led me to talk about other things. So I don't know, it was long. For this one, you can skip parts if you want through the chapters, but I promise you it will be more fun to talk about the Poisson distribution if you have all these other things already in your mind. Before we begin, I want to propose an exercise that may sound a little bit silly for you, but it's going to be helpful, so pick up a piece of paper and copy the picture. The exercise is that you are supposed to complete the pattern in the following way. Every time that you see 2 numbers side by side, you add them up and write the answer in the next line, sort of between them. So 2 plus 1 is equals 3, 3 plus 1 is 4, 3 plus 3 is 6. Just continue going on in this way. Pause the video and then compare your answers to mine. Hopefully we have all the same numbers. I have stopped on the line of the number 8, but of course this is an infinite thing, right? You can keep going on for as long as you have the patience to do so. And this is a very common pattern. It has a name. This is called Pascal's triangle. I am going to have to erase it now to continue the video, but of course you've done it on paper, so keep it close to you. You're going to want to compare it to something else later. So here is the second exercise. So we're going to want to take x plus y to the power of various things. The list is going to keep going on, but looking at just these for now, x plus y to the power of 0 obviously is 1, just like anything to the power of 0. X plus y to the power of 1 is just x plus y. And x plus y to the power of 2 is a very common mistake that a lot of people just write down x squared plus y squared, right? Of course, that is not correct, which is something that a lot of people actually know by heart. It's called a special product. X plus y to the power of 2 is equal to x squared plus 2xy plus y squared. The next one that I want you to do is x plus y to the power of 3, which is not something that a lot of people know by heart. And I'm not suggesting that you should, okay? If you memorize it, fine, but you don't have to. What I really want you to do is to think about this power of 3 as the repeated multiplication that it is, but don't write out the x plus y 3 times. Instead, you're going to write it 1 time and then multiplying by the power of 2 that you already had before. And now I want to do the distributive again, but with these terms. And this line over here is the final answer for x plus y to the power of 3. And now I want you to pause the video and keep going with this exercise in the exact same way. Pause the video and go do that. When you come back, I'm just going to have all of these 3 answers here. Okay, so here are the answers. I'm going to get out of the way so that you can see everything. It may be the case that we have the same terms just in a different order, so keep an eye out for that. The order in which I chose to write my terms is that I begin with the biggest exponent of x, and then I go down by the exponent of x. So if you look at the last line, it starts with x to the power of 6, and then it has a term with x to the power of 5. The next one is x to the power of 4, 3, 2, 1, and then no x's at all. Okay, so it's convenient to write them down in this order. So have you seen it yet? Have you figured out what the connection is between these 2 exercises? There are the same numbers. Look at your Pascal's triangle in your paper. But I still want to put 2 more lines on this list. I want to put x plus y to the power of 7 and x plus y to the power of 8. But I don't want you to spend all of that time doing all of the distributives now. Now I want you to use this new trick that you've just learned, which is just as much as a lot of people know x plus y to the power of 2 by heart. So when you see that in the middle of a calculation, you don't really have to expand it and do distributive. You can just write this because you know the answer by heart. You probably don't know these other answers by heart, but that doesn't mean that you need to do all of this work explicitly like you did just now. This was an exercise. But in the middle of a question, I hope you can do it faster. And that is the trick, is to remember the Pascal's triangle and to just write out the answer. Remember to put the terms in this order, okay, with the descending exponents for one of the variables, which in my case I'm doing it with x. So if you know that you need x plus y to the power of 7, you just take a little bit of paper and write down 7 lines of Pascal's triangle. Then you will have that row of numbers at the bottom. Those are the numbers that you know you need for the expansion that you're looking for, and then you just write down the answer. I think that's the faster way. There you go. Please compare that to your answers to see if you have learned how to do this properly. That is all there is to it. This is the binomial theorem. So in order for them to put that into the formula booklets to help you even more with this, even though it is a simple and small topic, the problem is that it needs to turn into a formula. And when we take that whole process that we've just studied and try to write it in mathematical notation as a formula, I think that that is probably the thing that is confusing to a lot of people and is making you think that this is a complicated topic when it really is not. So let's think about, from the point of view of the people who are writing the formula booklet, how can I put that in the booklet? I can't just put a formula for x plus y to the power of 8 like the one we just did, because 8 is an arbitrary number, right? I want the students who have this booklet available to be able to do that for any number, not just 8. So the first thing that they need to do is to take away that specific number 8 and put a variable in its place. Let's call it n. And it's always going to start with that 1 from the Pascal's triangle, which in our case is going to be 1 as a coefficient of x to the power of something, n. So the first term that I'm going to write down in my formula is x to the power of n. And then I know that the last one is going to be y to the power of n. But before I get there, I need to go through a few things first. And if you're looking at the Pascal's triangle, you can see a pattern that the next term, the thing that comes after the 1, is this one here, which in this case was 8, but the previous one was 7, 6, 5, 4. So the next one is just going to be n. So here I have n as a coefficient, and this term is going to have x to the power of something and y to the power of something else. This is my second term in my expansion, like the ones that I did explicitly in the previous board. And I mentioned that the order in which it is convenient to write those terms is in descending exponents of x, right? So if the first one is x to the power of n, the second one is x to the power of 1 less than that, so it's n minus 1. And maybe you've noticed that before in the previous examples, that when the exponent of the x is decreasing, the exponent of y is correspondingly increasing. So this one is y to the 0 because there's no y here. This here is y to the 1. The next one is going to be y to the 2. But I still don't know what the coefficient here should be. And actually, I know what the coefficient is the next number in the Pascal's triangle. The only thing that I don't have yet is a name to call it by in order to write my formula. So now is the time when a mathematician creates a name for the thing that he wants to refer to. In the formula booklet, this is called by this notation. You can read it and choose to. I'll talk about the reasons for calling it that a little bit later on. Just know that there are other possible notations that you can write this in. A very common one is this parentheses with a stack of 2 numbers over there. This is just a curiosity at this point because the one that you need to recognize is really the one in the formula booklet, right? So that is the name that we are going to call all of the numbers in Pascal's triangle. And now I want to talk about rows and columns in Pascal's triangle, but it's kind of weird to talk about columns when it's written diagonally like this. So I'm going to erase my triangle and just write it down a little bit shifted like this. So there you go. You can see that there are still the same numbers. If you're writing it out in this format from the beginning, just pay attention who you're adding to who, because now it's like this plus this equals 6. this plus this equals 20. It has to go sideways a little bit. So now that I've rewritten it this way, it's easier to talk about rows and columns. I started with row 0 because I want the name of the line to be the same as the number who is here, right? So for this to be row 6, this needs to be row 5, and this is row 2, row 1. The first one needs to be row 0. Now I want to do the same with the columns. So I've started with column 0 as well, okay? And the thing that we were trying to point to a particular number in that table of numbers by our notation, let's pretend that we're talking about n equals 6 right now, just because it's a line that we have here. So we are talking about 6 choose 2, which is supposed to be the number in Pascal's triangle, which is in row 6, column 2. So it's that number over here, which is where having notation really comes in handy. And now the next one is just going to be the same, right? It's not going to be n choose 2, but it's going to be n choose 3. And I've also followed the pattern in the exponents. So the exponent of x was going down as n minus 1, n minus 2, and minus 3. The exponent of y was going up, like 1, 2, 3. And then I just did plus dot 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 and plus the last term finally, which we mentioned was going to be y to the power of n. So x plus y to the power of n is a sum of many terms. I know that the formula booklet doesn't do that, but I'm going to write that using sigma notation. So x plus y to the power of n is a sum of many terms. Each term looks pretty much the same. It starts with a binomial coefficient, which are these numbers that belong in the Pascal's triangle. So it's always going to be n choose something. After the n choose r coefficient comes x to the power of something. There's an r here. So here it's n minus r. And the exponent of y is r as well. There you go. That's the formula. So this number n choose r is also in the formula booklet by itself. It has a formula to calculate it by hand. And if you are in a paper 2 question, then your calculator also has an n choose r button that you just put the n and the r, it gives you the answer. But for paper 1, if you want to work with somewhat large numbers and you think it would be too much work to write out enough lines of the Pascal's triangle, then you have this formula to work with as well. But I don't really see much difference between what we know if we are typing something in a calculator or if we are plugging numbers in a formula without understanding why the formula is the way that it is. Those things are equivalent conceptually. Of course, the calculator makes it faster, but plugging numbers into a formula that you don't understand and calculating by hand, even though it takes more time, doesn't mean that you know more math. You're still just plugging things into things. So I want to talk about the formula a little bit, and it's going to make more sense if we talk about why is this number called n choose r? What is this about choosing? So the thing is that this is a number that represents in how many different ways can we choose r things out of a set of n things. So for example, if we have this little bag here with 7 different colored balls and we want to put our hand in the bag and pick out 3 of them, so that's 7 choose 3. There are different ways to pick 3 balls out of there. You can get the green, the red, and the orange, or the purple, the pink, and the light blue. If you write out all of the possible ways, you will find the number 7 choose 3, which is this number here. 7 factorial is 7 times 6 and times and all the way to 1. And then we have the 3 factorial, which is here. And 7 minus 3 is 4, so we also have the 4 factorial right here. A bunch of things cancel out. 3 times 2 is 6. And the answer is 35 different ways to pick 3 balls out of that bag of 7. And this is relevant for the problem that we've been talking about, because, for example, when you want to do x plus y to the power of 7, one of the terms that you're going to find is x to the power of 4, y to the power of 3 with this coefficient. And that happens when inside of all of the distributive that has to happen here, from these 7 factors, you just happen to pick out 4 of them to be x and 3 of them to be y. But which ones are the y's? So you have 7 possibilities, out of which you need to choose 3 of them. And the number of different ways to make that choice, I've underlined one of them here in red, but the number of different ways to make the choice is 7, choose 3. That's why the number is called choose, because you have 7 things and then you want to choose 3 of them, in this case, to make them into y's in the distributive. The 4 that you haven't chosen will naturally become the 4 x's in this term. And that's why this coefficient needs to be here. So finally, the reason why the factorials are coming up is because of the way in which you make that choice. Like, which 3 out of these 7 things am I going to choose? First, you choose one of them, so you have 7 choices. So that's 7 ways in which you can choose the first one. So let's say I chose this one, and then I have to choose the second one, but I can't choose the same one again because that one is already decided. So out of the 6 remaining things, I pick one. So that's 6 ways to make that choice. I picked this one. So now these 2 are already taken. I have 5 left, and I am going to pick one of the 5, which it was this, but I had 5 different things to choose from. So now I have 3 y's out of the 7 binomials being multiplied here. But the thing is that it doesn't matter if this was the first, second, and third, the way that I described it, or if I picked this one first when I had 7 choices, and then when I had the other 6 choices, I happened to pick that one or this one, and then the third choice was the other one. So there are 7 times 6 times 5. Some of those are the same, like this is the same as this. And so I don't really have this many choices. It doesn't really matter which one of the 3 was picked first, so that's division by 3 here. And even considering that this was the first one, I still had first this and then that, or the other way around. So that's 2 different choices that give me the same final set of 3 y's. That is the number of choices, so that's 35. But in order to generalize this for other numbers, it makes sense to put a 1 here, just because then you have 3, 2, 1, which is 3 factorial. So it's nice and easy to write without knowing that it was a 3. If you have an r here, then you're just going to write r factorial. And I want the same thing for the top. I don't want to write 765. I actually want to put the 4, 3, 2, 1 here to make it into a 7 factorial, so that whatever n is there, I can say n factorial without knowing what n is. So that's good to make a formula, but I can't just put 4, 3, 2, 1 here without also putting them in the denominator to cancel out. And that's how you get the n minus r factorial that is in the formula. So you notice that the n minus r factorial part, it always cancels out with part of what's in the numerator, and whatever remains here is always the same amount of numbers on the top and on the bottom. What's interesting is, why are these numbers in the Pascal triangle? And to answer this question, we need to remember the way that the Pascal triangle is built, which is each number is the sum of the previous 2 numbers on top of it. So we have to write down this relationship and just check if those numbers follow the same relationship, then they're going to be the same numbers because they are starting at the same place, which is the number of possible ways to choose 0 things is always just one way, which is don't choose anything. And the number of possible ways to choose all of the elements that you have, like 7 choose 7, is also just one way, because it's just choose everything. So the sides of the triangle are already matching by definition. So if the insides are both following the same structure on how to build the next one from the previous ones, then they're going to be the same all the way through. This is a form of proof by induction. So let's write down exactly what it is that we are trying to prove here. The number that is 2 numbers added, let's call him n choose k, like the most generic one. And one of the numbers that is being added is in the previous row, so it's n minus 1, but it's in the same column, so it's k. And the other number is also in the previous row, n minus 1, but then it is one column to the left, so it's k minus 1. What we are trying to prove is if for these numbers n, k, with that formula up there, does n choose k always equal n minus 1 choose k minus 1 plus n minus 1 choose k? That's what we want to prove. And this proof is going to be disappointingly algebraic, meaning that there is no mystical, wondrous thing that is going to happen to clarify in your mind a deep reason behind why those numbers should be there. It's just going to be a calculation that works. So over here, n minus 1 choose k minus 1 has this part here. Now I need n minus r, which is the top number minus the bottom number. The minus 1s cancel out. This is n minus k. Over here, I need n minus 1 minus k. I'm going to write it as n minus k minus 1. And I've just realized that I've switched my notation from r to k at some point, right? So I fixed it up there. Now it's all k's. Right, so this is two fractions that need to be added. I need them both in the same denominator. Notice that both denominators are a product of a bunch of things, and a lot of them are already the same, but there are two differences, two small differences. First of all, over here on this one, I have a k minus 1 factorial, and this product on the other one goes all the way to k. So if only I could have an extra k in this one, the first part would be k factorial, which is the same as in the other one. So I'm going to solve that problem by multiplying this first fraction on the numerator and denominator by another k. And then I kind of need to do the same thing on the other one, because this is n minus k minus 1. The next number in that product would be n minus k, which is the one that this fraction goes up to. So I'm going to multiply that one on the top and on the bottom by n minus k, and I will have both fractions in the same denominator. So now I'm just going to add them. And notice that as a result of that, the numerator of this new fraction has an n minus 1 factorial that can be factored out. And when I factor it out, it's going to be multiplied by k plus n minus k, which is just n. Well, but there we go. That's what we wanted, because n times n minus 1 factorial is n factorial. So that's it. Both sets of numbers follow the same structure to produce the next numbers, so they are always going to be the same numbers. So I find that disappointing because it's too algebraic and blind, but there is another way to look at it that I actually like a lot. When we go back to thinking about 7 choose 3, in how many ways can I choose 3 out of these 7 factors? Well, in some of the ways that I can do that, I will have picked the first one to be a y, and in some of them I will not. So I want to look at these possibilities separately. In one of them, I have chosen the first y, and in the other set, I have not chosen the first y. And every one of the ways to pick 3 y's is going to be one of these two things. There is no third option. You either have the first one or you don't. So if you have the first y, like I have him underlined in red here, then I need 2 more. And these 2 need to come from the 6 remaining factors. So that is, in how many different ways can I pick 2 out of the 6 remaining factors? That is 6 choose 2. But if I haven't chosen the first y, and more than that, I have decided that I am not going to choose him, so I'm actually going to choose that x, but I still need 3 y's. So where are they going to come from? They are going to come, all 3 of them, from the 6 remaining factors. So in how many ways can I do that? 6 choose 3. And of course, I'm doing this here in an example of 7 choose 3, but you can do the same with the letters n and r. So for any n there, you choose or don't choose the first one, and you have n minus 1 remaining ones to put here, and you are trying to choose r things. So if you don't choose the first one, then you still have to pick the r things from the rest. But if you did pick the first one, then there is one less thing that you need to pick. So it's r minus 1 right here. And that is exactly the same relation from the Pascal's triangle. So this is what explains why the choose numbers are the numbers that appear in the Pascal's triangle. So you can use this formula if you want because it's correct, it makes sense. But if you feel more comfortable, you feel like you can write the triangle faster than you can do this, then you can do that as well. All right, so finally here is the binomial distribution. It is about repeated trials and number of successes. So here's a very typical example. My variable x has a binomial distribution with 10 trials, and the probability of success in each individual one is 0.2. So I'm asking you, what is the probability that the number of successes is going to be exactly 3? Well, which 3? Is it the first 3 of the 10? Is it the last 3? Is it 3 spread out trials out of the 10 repetitions that I'm going to make? In how many different ways can one choose which 3 of the 10 trials are going to be successes? 10 choose 3. Of course, the probability can't be 10 choose 3, right? Because that's not a number between 0 and 1. But the thing is that I still need to multiply by the probability of that actually happen. Each one of these 10 choose 3 setups of like these 3 are successes, those 7 are failures. They have exactly the same probability of happening because in any case, the 3 that are successes, each one has 0.2 probability of actually being a success. So this needs to be multiplied by 0.2, 0.2, and 0.2. That's the probability of success for each one of the 3 trials that you selected to be successes. But the failures also need to be accounted for, because if I don't do anything about the failures, I just leave it open like that, then maybe the failures aren't actually going to be failures, right? They could be successes as well. So you do need to put a 0.8 there. In fact, you have to put a 0.8 for each of the 7 failures. And that's it. That's the probability of x being equal to 3 in this binomial distribution. Really, that's all there is to this connection. I can write the general version of it without being an example. So this is in how many ways I can choose k out of the n trials to be the successes. Then k of them needs a probability of p of being a success, and the rest of it, the n minus k, has the 1 minus p probability of actually being a failure, which was the 0.8 up there. But notice how much this looks like the binomial theorem. It doesn't just have the same name, it looks exactly the same. It has a binomial coefficient, it has something to the power of k, something to the power of n minus k, exactly like the other thing. In fact, you can write something silly as 1 equals p plus 1 minus p, and then you can put it to the power of n and expand that side by using the binomial theorem, where it's this thing plus this other thing here. And it's going to look exactly like that, with the sum, of course, because I'm putting all of them, not just the probability of x being a specific number. Because that's the thing. The sum of your random variable being all of the values that it can possibly have, which in this case are from 0 to n number of successes, the sum of all of those probabilities needs to be equal to 1, like every probability distribution. But in this particular case, this 1 can be split up in these ways, which follows the binomial theorem for writing it in this weird way here. So this formula for the binomial distribution is not in the formula booklet, but it is what we are going to use right now in order to talk about the Poisson distribution, which is why I've just spent like half an hour talking about it. The only things that appear about binomial distribution in the booklet are these formulas for the expected value and the variance, and we are going to use them, but we're also going to use the other one. As for the Poisson distribution, this is only part of the AIHL course. So the other courses don't touch on this topic at all. But even if you are taking one of those courses, it's still an interesting tool for you to know about. Maybe you want to use it in an IA if you're studying a situation that calls for it. But the thing is that you're not going to know if the situation calls for it if you don't know about it. So that's always a very good reason to learn more stuff. Anyway, In the formula booklet for the AI course, there's also not that much information about the Poisson distribution. It's very similar. They tell you the expected value and the variance. So we can infer from this that the Poisson distribution only has one parameter and the expected value is the same as the variance. But we are actually going to prove that during our process of proving many other things about it. So my favorite type of situation to explain what the Poisson distribution is about is think of a soccer match, and the random variable that I'm interested in studying is the number of goals that happened during that soccer match. So we are talking about a discrete random variable, which is the number of goals. You're not going to have half a goal. And throughout this explanation, I am going to be assuming that the expected number of goals during a soccer match is 4.5. Okay, that was just an arbitrary choice that I made because I think that the calculations are going to be a little bit easier. Right, so if we don't have any other options at this point, if we don't know about the Poisson distribution or why it should be the adequate way to deal with this situation, we are probably just going to do the best that we can. And the only other discrete random variable that we know right now is the binomial distribution. So let's see if we can kind of make it fit. The binomial distribution deals with a repetition of trials and the question of how many of those trials were a success. So you could think of the 90-minute soccer match as being like 9 intervals of 10 minutes. So when I say 9 intervals, that's already a repetition, right? I'm going to do something during those 10 minutes, and then I'm going to repeat it 9 times. And then if I say that the probability of a goal happening during those 10 minutes is a half, then the expected value over the 9 times 10 minutes is going to be a half times 9, which is 4.5. That's why I chose the number 4.5, because then I can use P equals a half for this first attempt. That's about all that we can do with that, with the formulas that are in the formula booklet. But if we take into account also what we know about the distribution in terms of the binomial coefficients and all of that, we can also answer questions like, what is the probability of there being no goals in the match? What is the probability of there being 3 goals or 5 goals? But here's the problem. If we model the soccer match this way, we are limiting the maximum number of goals that are possible. And although 10 goals inside of one match is kind of rare, there's nothing in the situation itself that is preventing that, right? The game could be 5 versus 5, or it could be 10 versus 9, or whatever. You can have 19 goals in a match, and this kind of modeling does not account for that. So the first thing that you could think in response to that was, well, but then again, there don't really need to be 10 minutes in between 2 successive goals, right? Maybe there's less. So the goals are coming faster, so you can fit more goals inside of the same match. So what if instead of 9 intervals with the probability 0.5 of having a goal in there, what if we broke it into intervals of 5 minutes and said that the probability was 0.25? That's not going to change the expected number being 4.5. It changed the variance a little bit. Okay, so in theory, you could keep doing that, right? You could say, well, 5 minutes is not a short enough amount of time. Maybe you can score 2 goals in 5 minutes. I know that it takes a little time between 2 goals, like they have to celebrate and they have to go back to the center and set up the thing to start again. Maybe it takes a little bit less than 5 minutes, but that's not going to happen in a lot less than 1 minute, right? So you could do this in 90 intervals of 1 minute and say that the probability of a goal being scored within that 1 minute is 0.05, you would still have the same expected value of 4.5. So I've just put those numbers here, and again, see, of course, the expected value is not changing because we're doing this on purpose, but the variance has changed again, and it has gotten closer to the expected value. So already you start to see what may be happening to create a Poisson distribution here, because remember, the hint that the formula booklet gave us was that the Poisson distribution has this feature where the expected value and the variance are the same. We're not really seeing that here, but this is suggestive that we are going in that direction if we just keep breaking the intervals into smaller and smaller pieces. We started with an interval of 10 minutes and they were really quite different. One was half of the other. And then the other one that I had here, the variance was already 3.4, I think. Now it's 4.3. It seems to be getting closer to 4.5. And that's exactly what I'm going to try to rigorously prove. So although this is my favorite example, the soccer match, it's not the only type of situation that you're supposed to recognize as a Poisson distribution exercise. If you are in the AI-HL course, then that's something that you're supposed to be able to recognize. Anything that has something happening at seemingly random intervals, but with a fixed rate of occurring. So like it would be in a soccer match, we have approximately a goal happening every 20 minutes. One goal per 20 minutes is a rate at which this event is occurring, right? The goal being scored. Of course, it's not going to be like on the dot, 20 minutes a goal, 20 minutes a goal. It's not like that, but on average, if it takes 20 minutes for there to be a goal, then on average, the matches are going to have 4.5 goals and all of that is going to happen. But anything that has something interesting happening at random intervals, but with an average known rate, that's when you recognize the Poisson distribution. Another very typical example is like people arriving at a train station. And maybe the train station example illustrates something that the soccer match doesn't really illustrate because of the necessary time between one goal and another goal. Okay, so you're never going to have two goals being scored at the same time, obviously, because there's only one ball in the game. And also, you do need probably at least a minute to set the game up again and be able to have the next goal. So for the soccer match, really, this binomial distribution here is probably enough. You probably don't even need the Poisson distribution for the soccer match if you're willing to have a binomial with 90 repeated trials. But for the train station, that's different because the people can arrive at the train station at the same time. You imagine the door, the entrance, it's big. Like I can have 5 people walking through the door at the same time, and then 5 minutes go by and nobody else gets there, but then someone and then someone else again, then a pair of people. So you can still calculate the average rate at which people are arriving at the station, but you don't have this restriction of it not happening at exactly the same time or there being a minimum interval between two occurrences, which in the soccer match you kind of do, but not for arriving at the train station or any of the other situations that you might see in exam questions. Because here's the thing, the Poisson distribution, just like the binomial distribution, they are both discrete random variables. They are not continuous random variables, right? So it's important for you to know the difference between discrete and continuous. But there is an essential difference between Poisson and binomial here, that although both of them are discrete, the Poisson distribution is kind of dealing with something that is continuous, and that is time. Time is continuous. So the number of events that you are observing, like the number of goals in the match or the number of people that got to the train station, that is a discrete variable. But we are also interested in the rate at which that is happening. When we say a rate, that involves time, and time is essentially continuous. So there is this middle ground here. And after this philosophy session, what I'm going to do is try to do this in general, okay? Instead of 9 or 18 or 90, I'm going to put n, and then instead of a fixed number here, I'm going to put 4.5 divided by n, because then the expected value is going to stay at 4.5, and we'll calculate the variance and see what happens. Okay, so here it is. Obviously, the n's are going to cancel out. That was done on purpose. And we're interested in figuring out what would happen if we kept breaking up the intervals into smaller and smaller pieces. Instead of stopping at a minute, we can keep going. Time is infinitely divisible. That's what makes it a continuous variable. So we are interested in the limit of this as n goes to infinity. There are infinitely many intervals because they have become infinitely small. Obviously, this limit is 4.5, right? Because this thing here, the fraction is going closer to 0 as n gets bigger. So 1 minus 0 is 1, 1 times 4.5. And there we go. We have the variance being equal to the expected value, exactly like we wanted for the Poisson distribution. So that is the definition of the Poisson distribution, okay? The Poisson distribution is what happens to the binomial distribution when you keep splitting the thing into smaller and smaller intervals going to infinity. But just finding out the fact that the variance then becomes equal to the expected value, we want to learn how to calculate the probability of the number of goals in this match being equal to a fixed number like 3. We want to have an actual formula for that. And for that, we're going to use the actual formula that we have for the binomial distribution. We want to be able to answer questions like this one, the probability of there being exactly 5 goals in the match. Okay, so everything that I just said is now translated in mathematical notation up here. I'm calling my variables, I'm not just calling them x right now because I want to have a lot of them. So in order not to repeat my names, I'm putting a subscript with a number. So like x9 is the binomial distribution with 9 intervals and probability 0.5. And then there's going to be an x90 and x whatever. And then I'm defining x infinity here. And I do have to define that, okay? It's not enough to say all the x n's and then say like, now let n equals infinity. You can't do that because infinity is not a number. But you can define x infinity to be the limit as n goes to infinity of the distributions x n. So that's what I'm defining here. And then I'm saying that this limit, this distribution x infinity, is what I'm going to call the Poisson distribution with that expected value of 4.5. Over here I have the first example, which is x9, and I'm calculating the probability that x9 is equal to 5. So 5 goals in the match. And for that, I'm using the formula for the probability of a number in the binomial distribution, right? That's what I mentioned in the beginning of the video that we were going to need. So we have 9 choose 5 over here. This is a little bit confusing for this example because they're both 0.5, but this one is p and this one is 1 minus p. It's going to be more obvious in the next ones. So 9 choose 5 is like which 5 of the 9 10-minute intervals had a goal scored in that interval. Probability 0.5 of that happening in that interval, so to the power of 5. And then probability of the goal not happening in an interval to the power of 4, which is the number of intervals in which I did not have a goal. Put all of that in the calculator, you get 0.2461. Now let's do it with 90. So again, I've just plugged it in the formula, and like I said, now it's more evident the difference between these things because the probability of having a goal in a 1-minute interval is 0.05, and the probability of not having a goal in that interval is 0.95. Of course, there's a lot more of the minutes where there isn't a goal. Only 5 of them actually had a goal for the probability of x9 being equal to 5. And then you put everything in the calculator, you get 0.1755. It has gotten quite a bit smaller. Like, that's not obvious at all. It's just a thing that we see in the numbers. But when I put the 900, which is the next one that we're going to see, you'll see that the difference is going to be a lot smaller because this thing is converging to somewhere. So here we see this happening, like the difference is much smaller. You see that it wants to go somewhere, it wants to converge to a number, so it has to slow down. But that was the last concrete example that I was going to do before doing it in generality with n to see what happens. So write down the numbers if you want, because I'm going to erase them. Nothing very surprising here. I just plugged in n and 4.5 over n for p. Be careful with the notation because this actually is a fraction inside of a parentheses, and this is not, right? This is the binomial coefficients. But what's going to be interesting now is when I ask for the probability of the Poisson random variable being equal to 5 by doing a limit of this expression as n goes to infinity. I'm going to move to the corner here so I'm not in front of the math, but I've put the limit here, and then I've already substituted the binomial coefficient n choose 5 by its formula. This is just the n choose r formula that you're used to, except I've already canceled out the n minus r factorial from the top and from the bottom. Okay, so in this case, it was an n minus 5 factorial, which was here and here. I've canceled those out. What remained was 5 terms on the top and 5 terms on the bottom, as usual. Then I took that fraction with the power of 5 and I just split it up, the 5 on top and the bottom, did nothing to this final term here. And now I'm going to do a very interesting move. So pay attention, because I'm not going to rewrite the whole thing. I'm going to erase some and put them someplace else. I'm going to take this 5, 4, 3, 2, 1 here, which is 5 factorial, and I'm going to put it here instead. And this n to the power of 5 I'm going to put over there. So I can do that because it's a fraction times another fraction, so you're just multiplying anyway. I'm going to switch their denominators. That is going to be very useful, because remember I said we had the same number of terms in the numerator and the denominator, 5 terms, and we also had 5 n's here. It was an n to the power of 5, so I'm able to match 1 with 1 here. Here I just wrote it as 5 factorial, but now I want to split up this fraction into 5 fractions. That is a very interesting move, because listen, of course the first one is n over n is just 1, because the n's cancel out, and that doesn't happen with the other 4. But if you think about the fact that I'm pulling a limit as n goes to infinity, they kind of do cancel out. Because as n goes to infinity, n minus 1 and n is basically the same thing. And you can do this in a much more formal way by multiplying the numerator and denominator by 1 over n and all of those things that you learn how to properly take limits. But this is what's going to happen, right? This is just going to be 1. The fraction doesn't cancel out like the other one did. That's not what I'm saying. What I'm saying is that the limit as n goes to infinity of this fraction is 1. But the limit as n goes to infinity of this fraction is also 1, and this one, and this one, because n minus 4 and n, also the same thing, because n is going to infinity. And then if you're thinking of questioning this, because I might just be lucky because 5 is a small number, so I'm just comparing n minus 4 with n, but what would happen if I was asking about the probability of it being a bigger number? Because I said that one of the main differences between Poisson and binomial is that binomial has a natural limitation of the biggest number that the variable can be. And Poisson doesn't have that. If you have a Poisson variable of expected value 4.5, it can be 4 million. Like, that's possible. It has a very small probability, but it's possible. So I wonder if n minus 4 million divided by n would also cancel out. But here's the thing, it does, because 4 million is a lot bigger than 4, obviously, but n is going to infinity. That 4 million doesn't stand a chance. N is going to be as large as it needs to be, so that the n minus 4 million over n actually does go to 1 as n goes to infinity. So this is brilliant. We can just get rid of all of these fractions because in the limit they're equal to 1. So what remains is the rest of the things, right? The things that you can see behind my head here. 4.5 to the power of 5 over 5 factorial, just a number. Where's the limit of n going to infinity now? There's only this one here with this. And listen, now I'm going to pull a card out of my sleeve, because this is a very well-known limit and I don't plan to prove it in this video, but if you want, please let me know. I can do another video about it. This is something that we know the answer to. We know the limit as n goes to infinity of this kind of expression is this. And now the minus 5 here didn't play any role, okay? Because as n goes to infinity, like we were saying, n and n minus 5 is exactly the same thing. So if you just ignore the minus 5, this is the very well-known limit that turns out to be e to the power of minus whatever is here, 4.5 in this case. Obviously, this is not specific to the numbers 4.5 or 5 that we were using in our example. This is a very general thing. If x is the random variable Poisson of parameter mu, then the probability that x equals k is mu to the power of k over k factorial times e to the power of minus mu. That's the result that we've just proved. Now, it wouldn't be necessary for us to take this formula now and try to calculate the expected value of the Poisson random variable, because this is kind of a circular thing. We started by definition with the fact that the expected value was this mu. But I'm going to write that down anyway because it's going to be interesting. So the expected value of the random variable is the sum over all possible values of the variable, which in this case goes from 0 to infinity, of the value times the probability of that value happening. So the first thing I see here is that there is a k and a k factorial, so that k can cancel out, leaving a k minus 1 factorial down here. Then in order to make these two numbers match again, I'm going to make this one into a k minus 1 by taking one of the mu's and putting it out here. But now the things that don't depend on k can get out of the sum. That's the mu and the e to the minus mu. And I forgot to say before, but I'm going to go back now. When there was that k here that we canceled with the denominator, that k actually means that this sum should have been starting in 1, right? Because the term with k equals 0 was a 0 that we were adding, so the 0 term doesn't do anything. I'm going to go ahead and change this k to starting at 1. Which really makes a difference down here, because if k is starting at 1, but both of the exponent and the factorial are k minus 1, so the exponent and the factorial are actually starting at 0. So I can change the names of my variables here so that it actually starts at 0, but I don't have k minus 1 and minus 1 here. I just have k. So that looks like that. And this thing here is a very well-known thing. It's just the Maclaurin series for the exponential, which means that the term circled in green just becomes e to the power of mu. That cancels out with the e to the minus mu that we had before. And the expected value of the random variable is just mu. Like I said, we didn't need to prove this. It was just a fun thing that I wanted to show you. What we can and should prove is the variance. Because way in the beginning, when I did 3 examples with 990 and 900, it kind of looked like there was being some sort of asymptotic behavior. It was slowing down its change, but we didn't prove anything, right? At this point, we think we know that the variance is equal to mu, but we don't really know that. It's just written in the formula booklet, and that's what this video is all about, explaining why it says that over there. So that is important for us to prove right now. I've just written the formula here. The variance is like the expected value of the differences squared, right? So the probability of each of the infinitely many results multiplied by the result, the distance from the result to the mean squared. First thing I want to do here is actually to expand this k minus mu squared. I'm going to do that, but as I go to the next line, I'm already going to split it up into 3 sums, because this is going to have 3 terms. So instead of having a parenthesis inside of one sum, I'm going to put one sum for each of the 3 terms. And in each one of them, I am going to take out the things that don't depend on k. The e to the minus mu was the same for all 3, so I just put it out there. Now we're going to cancel some things. For example, this one here is just e to the mu, like we have just mentioned in the previous page. This one also does a similar thing to the previous one. We don't want to start at 0 because of the k0 here, so we start at 1. Then we cancel out the k with the k from the factorial by making it into a k minus 1 factorial. Then we take one of the mu's and put it outside, so this one's going to be squared. Now we switch our variables again to go back to starting at 0 without having these minus 1s here. And the result is that we have another e to the mu. The third one is a little more interesting, but I'm going to show you. I just don't have enough space here right now. So for now, believe me that this one is equal to this. I'll show you in a minute. And let's see everything that cancels out here. So as for the mu squared, we have one of them here, another one over here, also multiplied by e to the power of mu. And then we are subtracting 2 of those here, 2 mu squareds, also multiplied by e mu. So all of that cancels out. Everything that remains is just this, the e to the minus mu multiplied by the mu e to the mu. This one cancels with this one, and then the variance is just the remaining mu. Okay, so to explain the one that I didn't explain yet, here's a trick that I really like. That's the Maclaurin series that we are used to, right? It's e to the power of x. Now, the first thing that I'm going to do is to take the derivative of that. The left-hand side is very easy because the derivative of exponential is just itself. And the right-hand side, it looks like a polynomial. It's not a polynomial because it's infinite, but it is an infinite sum of power terms. So I can just take the derivative inside of the sum as if it was a polynomial. Now this time, instead of canceling this, I'm actually going to leave it there because the thing that I'm trying to go towards is a thing that has not just a k here, but a k squared, right? So I don't want to remove that. I want to keep it there and see if I can come up with a second one to make it a square. So instead of canceling that, I'm going to multiply both sides of this equation by x. I'm going to put an x here, and multiplying by x is just going to get rid of the minus 1, right? Everybody's going to get an extra x. Now I have this, and I'm going to take the derivative again. Over there, I am going to use the product rule. On the right-hand side, again, I'm going to take the derivative inside of the sum. So this k is going to multiply by that k, making it a k squared. That is almost exactly what I want. The only thing that I don't want is this minus 1 over here, but I know how to get rid of it. It's by multiplying both sides of the equation by x again. So I get rid of the minus 1 here because everybody got multiplied by x, but I need to multiply the left side of the equation by x as well. So there you go. That was the other result that I used to prove the variance. And that's it. We can say that all of this video was just for fun. Like, honestly, Poisson distribution is only in the AIHL course, and even there, all that you have to do is recognize the situations and ask for the probabilities in your calculator, so you don't really need any of this. But like I said in the beginning, that's not really what this was about, right? In this particular video, I'm not trying to help you solve IB questions from exams. I am actually trying to tell you what the Poisson distribution is, where it came from, why it behaves the way that it does. So now you know. So naturally, I wanted to put this to the test by writing an IA, and I used the example of very recent soccer matches in the World Cup, which are very interesting and kind of easy to find the data online about the number of goals that were scored in a large number of matches. Motivation for using the Poisson distribution to describe the numbers of goals in a match, and how that comes from the binomial distribution with smaller and smaller intervals and so on and so forth. So that's exactly what I'm going to do with this data. I'm going to use the different distributions and I'm going to compare them to see which one works best. And then when I listed here the 4 distributions that I'm going to be trying to fit to the goals data, as it is right now, I did get to explain 2.6875 before I even typed the distributions, which that number is the average number of goals per match according to the calculation that I just did over there. But that number of 3.5 something is explained here in this next paragraph. It is the variance that I got from the data to make the second normal distribution. And this is going to be interesting because I'm going to talk about degrees of freedom very shortly to do the chi-squared goodness of fit tests. And it's an interesting discussion about when and why you lose these degrees of freedom. Now let's go back to the table to talk about this other thing that's also mentioned here, that is the expected values being less than 5, right? And I don't know, I kind of don't like combining categories too much, especially combining the categories of 0 goals or 1 goal. It feels like a soccer match is so different when it's 0-0 or when it's 1-0. Those are not categories that I would choose to combine, but the data is in some way telling me that I have to, so I did both. And the results were not very different. You'll see, it's an interesting thing to compare. Interesting results, big p-values for all of them, but the Poisson were the biggest ones, which makes me happy, right? Because that's what I was trying to show, that Poisson is the most appropriate distribution for this kind of situation. So